These examples up here highlight a few important things that I wanted um, to segue us from Lewis structures into something called resonance. So we have the hypobromite ion. This is not one of the ions that's covered in your textbook. It covers hypochlorite. But I reminded you guys back in like module 2 when we were learning about ions that the chlorite and chlorate family, you should know their relatives, the bromate and bromites, iodate and iodites. So this is hypobromite. And drawn correctly, it's got 3 lone pairs of oxygen, 3 lone pairs on oxygen and 3 lone pairs on bromine. But there is another form that someone may draw which keeps 3 lone pairs on bromine, but brings oxygen down to 2 lone pairs. So we're going to talk about the difference between these two, and why one of them is a more realistic version of the actual molecule. And then over here we have nitrogen dioxide. This is a pollutant, and it highlights an important thing that I forgot to mention in our last class as well. We talked about electron deficient species. Do you remember the most common electron deficient species? This is the atom that actually prefers to have 6 electrons around it rather than obey the octet rule. B, boron. And then we have these expanded octets, hypervalent species, and this is a much larger family. How do we generally identify something that can expand its octet? Jordan? Specifically, if it has a D subshell, exactly. So that we find with elements in row 3 and lower on the periodic table. That's phosphorus, sulfur, chlorine, bromine, iodine, xenon even. And then we get this odd one, which is the radical species. You all are probably familiar with the term radical. I think in today's political climate, we say, oh, they've been radicalized a lot, meaning that they're more reactive. They are harder to control. But you also have some familiarity with the word radical when it comes to your math background. The radical sign is what we use to take the square root of something. That's a radical. And actually, root and radical are related. Radical means the most fundamental, the thing at the beginning. Here, a radical species is a unpaired electron. And as you would imagine, unpaired electrons are very reactive. They like to find something else to pair with, some other electron to pair with. Free radical species in biology are talked about a lot. You want these things in your diet that can get rid of free radical oxygen species because those radicals can do a lot of things, a lot of damage. The most common radical species that we're going to see in general chemistry is nitrogen. And it's because of nitrogen's odd position, having 5 valence electrons, trying to get to an octet. So in nitrogen dioxide, you'll see that nitrogen actually doesn't obey the octet rule. It is electron deficient, but it's not electron deficient in the same way that boron is. Boron has pairs of electrons, but nitrogen is electron deficient by just 1 electron, creating this 1 radical electron. Now, sulfur here has expanded its octet. Bromine here has expanded its octet. Nitrogen is technically deficient, but in a specific way with a radical species. We could also go through this and look at formal charges, correct? If we look at hypobromite on the top, that negative charge of BrO- has to be on either oxygen or the bromine. Based on those common bonding patterns that we saw yesterday in class, which atom is holding the negative charge here, bromine or oxygen? And if the common bonding patterns aren't settled into your mind yet, we can use the equation, valence electrons minus dots plus bonds. And that affirms for us that it's actually oxygen that holds the negative charge here. In this version of hypobromite, which atom holds the negative charge? It has to be either bromine or oxygen. And since oxygen has used one of its lone pairs to share with the bromine, oxygen is kind of giving away some of its electrons. Bromine is taking on those electrons. So the negative charge here is seen on the bromine atom. What about in SO2? Do we have any formal charges in this compound? We don't. But we also broke the octet for sulfur. So we actually could have drawn this structure like this. One of the double bonds to one of the oxygens is given back to the oxygen. Sulfur goes from expanded to obeying the octet rule. Are there formal charges now? Tell me a formal charge you see. Just like in hypobromite, this form of SO2 has a negative charge on the oxygen. But this is a neutral molecule. Hypobromite is an anion. There's always a negative charge somewhere. This is a neutral molecule. I can't have a -1 charge in one place on a neutral molecule without a positive somewhere else to balance it. Where's the positive charge? It's not on the other oxygen because we said no formal charges here, so this oxygen's not changing. When we look at sulfur, our formal charge equation is 6 minus 1, 2, 3 lines, 4, 5 from the dots, 6 minus 5 plus 1 charge. These are both SO2. One of them has minimum charges. One of them has maximum charges. The one with minimum charges has expanded beyond the octet. And then we have NO2. Jordan, you might not have an answer to this, but was there any reason why you didn't draw the single bond to the oxygen on the left, the single bond to the oxygen on the right, and the double bond to the oxygen on the left?
Like switching the single and double bond? No, I didn't really have reasons, just how I drew it.
Fair enough. And also formal charges in NO2. Are there any? We know that NO2 is a neutral molecule, so if there are formal charges, they need to cancel out. Where do you see a formal charge? A negative on the oxygen that has a single bond, just like here, just like here. And I can't have a negative in a neutral molecule. Positive on the nitrogen. Again, 5 minus 1, 2, 3, 4. That nitrogen is electron deficient, so it does make sense that the nitrogen has a positive charge. All three of these scenarios have two different Lewis structures that are all valid. So how do we say which one actually behaves more like the molecule? And I hate to say this, but Lewis structures is like not real. They're a good way of showing how atoms connect, but they do a terrible job of actually telling us about a molecule's behavior. So this is like, you know, explain a molecule to me like I'm 5. That's what Lewis structures do. And this is why we can have 2 valid forms, because they're not perfect ways of representing structures. When you get into my organic class, I'll introduce you to molecular orbital theory, and that is actually a much better way to represent a structure. So this is the last part that we have to talk about in Module 9. This is resonance. Again, a term you've probably heard before, so I want to connect with what you already feel or think when you hear the term resonance. Outside of chemistry, what does the term resonance make you think of? Things that go well together, they resonate with each other? Sorry, I talked over you.
They like complement each other.
Complement, okay. Any opera fans? I always think of that opera singer that hits the resonating frequency of glass and can shatter the glass. But this idea of kind of on the same page, yeah, that resonates. And literally the same frequency, that is resonance. In chemistry, the best definition here is to say resonance is the movement or delocalization, in other words, and I'm going to say of electrons, but that's not totally true. It's a specific type of electrons. Actually, I'm going to add in the type, and we're going to talk about that type either at the end of today or at the beginning of Monday's class. And that's pi electrons. Pi like the Greek symbol pi. What this manifests as is 2 or more Lewis forms, Lewis structures, where the atoms are still bonded to the same atoms, but the placement of the electrons has changed. This is what we see in this image on the board. This is actually an ion that you are all intimately familiar with, whether you like it or not. Do you guys know the name of this ion? Could you extract its chemical formula from its Lewis structure? Not CO2 minus. Sorry. CO3 2 minus, and that is carbonate. Carbonate, like calcium carbonate, an important part in all of our lives. Notice how carbonate's Lewis structure can be drawn 3 different ways. We know that this -2 charge is found at this oxygen and this oxygen, -1, -1. But why do I have to place the charges on those oxygens and not the oxygen on the left? There is no reason. I could move that double bond around to any of those 3 oxygens. 3 Lewis structures that are all valid forms of carbonate. These individual Lewis structures are called resonance forms. We would say that carbonate here has 3 resonance forms. And none of them actually exist. Instead, the molecule exists more like a resonance hybrid. The resonance hybrid we can draw by kind of disobeying Lewis structure rules. Because again, Lewis structures are not real, they're just a helpful way to visualize molecules and how they're connected. So we can bend those rules a little bit to actually show us more of what the structure really looks like. For carbonate, CO3 2-, the resonance hybrid, it doesn't have single bonds to each of the oxygens. It doesn't have double bonds. Instead, it has a bond and a third to each oxygen. And then overall, a 2- charge. You'll notice that I'm not drawing in lone pairs here. And that's because on a resonance hybrid, lone pairs are much more challenging to assign to a specific atom. It is those pairs of electrons, those lone pairs, that move from one oxygen to the other oxygen. Or we might say those lone pairs of electrons are delocalized. It's a pair of electrons not found on this atom and not found on that atom, but found across the molecule on all of the atoms. That's how fun electrons are. Now, could you look at that and tell me that it's a bond and a third rather than a bond and a half or a bond and a quarter? No, because I wasn't trying to draw only a third of a double bond. But we know that that's what it is. Look at the carbon to oxygen bond here. Double, single, single. 2/3 of the time it's a single bond. 1/3 of the time it's a double bond. So the bond actually behaves like a bond and a third. So these are resonance forms. They are two valid forms of these molecules. And the question is, which of them does the molecule behave more like, or are they equal in terms of how the molecule behaves? So we introduced some rules for resonance. And these rules will be pretty simple. Step number 1, minimize formal charge. You want the resonance form that has the least amount of formal charge, even if that means that you need to make something electron deficient, even if that means you need to make something hypervalent, expand its octet. You will do that by minimizing the charges. So one example I want to give here is actually the boron trifluoride. You guys had this on your sheet from yesterday. This was on the back side, far left on the middle. There are two valid resonance forms, and we actually relate resonance forms by this double-headed arrow. This is one arrow, not two. It's one arrow with heads on either side. Some of you drew a structure like this. In which all of the valence electrons are there, and every atom has an octet. But fluorine doesn't like to make two bonds. When it does, it takes on a positive charge. And boron actually doesn't like to take on 4 bonds. because when it does, it takes on a negative charge. These are two valid resonance forms, but one is a major contributor to the molecule. One of them actually resembles how the molecule behaves better. Which of these is the more major contributor to the structure? Structure on the left. Minimum formal charges. Let's take our SO2 example. Turn to the neighbor next to you and decide which of these resonance forms the molecule exists more like and why. Stop it. A student that's new to Lewis structures might draw the structure on the right first without assigning formal charges and say, I've got octets everywhere, all of my atoms are in, I'm done. But is this structure on the right, which maximizes octets, the best form for the structure? Tell me why. It has formal charges. And I don't need to have formal charges for SO2. But it does mean I need to expand my octet. So atoms that can expand their octet will expand their octet in order to minimize formal charge. Deal? Rule number 2. Maximize octets. Whoa. Okay, that's crazy because actually in example number 1, we preferentially minimized the octet of boron in order to minimize charge. That's the priority. We don't try to maximize octets until after charges are minimized. Yeah? That's why formal charge is rule number 1. If formal charge was not rule number 1, if rule number 1 was maximize octets, this would have been a more major form. I don't have a lot of good examples for you on this because most structures already do satisfy octets pretty easily. So for the most part, if you've minimized formal charge, you have maximized octets most of the time. When you get into my organic class, I'll show you a lot more examples where that's not true. But for general chemistry, this rule is almost always met. Now the third rule is appropriate charge placement. What do you think that means? How can I place a charge appropriately?
Maybe you're not like switching up the formal charges, like make sure that you have the correct positive or negative on the right one.
We said here with hypobromite there will always be a negative, and we said here with nitrogen dioxide there will always be a positive and negative. So I can't inherently do anything with those formal charges, so I want to place them in the most appropriate place. Where's the most appropriate place for a negative charge? what property of an atom could we use to justify placing the charge? Ryan, what do you think? Where can I place the charge most appropriately? What character of an atom helps me decide that? Electron affinity, remember, is energy given off when an atom receives an electron. No receiving of electrons here. There's no change in where electrons are placed. So its cousin, electronegativity. Atoms that have higher electronegativity get the negative charge. Atoms with lower electronegativity get the positive charge. So let's come back to look at hypobromite. Which of these forms of hypobromite places the negative charge appropriately? Jacob? The one on the left? Tell me why. Good. Remember on your periodic table, electronegativity trends up and over, up and to the right. Now you can see that oxygen is actually a little bit further left than bromine, but it's much further up. So it becomes a bit of a compounding effect, right? Which one plays a bigger role, being further right or being further up? Both play a role. So you have to kind of cancel forces. Oxygen is 2 rows higher and only 1 row left. So it makes sense that oxygen is most likely more electronegative. That's the gamble. You can memorize those electronegativity values if you want to, or even take up space on your cheat sheet for the midterm, writing down a selection of them, the ones that are the most important, a lot of these non-metals. Same?
Could you also say that oxygen is the most electronegative since it's close to fluorine, and fluorine is the most electronegative?
Good question. Fluorine is the most electronegative, so oxygen's proximity to it makes it a very good candidate for being one of the next most electronegative. Absolutely. So, Jacob says the form on the left is a major contributor because it places the oxygen, places the negative charge on oxygen, the more electronegative atom. That oxygen wants electrons more than bromine. So the form where oxygen holds on to the electrons stronger the form where oxygen holds the negative charge, that's our major contributor. This is what the molecule looks like more. So now we look at our NO2 example. Double bond on the right or double bond on the left. How do we decide which of these forms is a more major contributor? Does one form contribute to the molecule more than the other? They're the same. Because formal charges are equal in both of them. I can't minimize the formal charges at all. I could maximize formal charge. I could take that double bond back to the oxygen, put a negative charge on oxygen and another positive on N, but that would not minimize formal charge. I have octets as much as I can on all of the atoms, nitrogen being my radical species and being electron deficient there. And I've got the charges placed appropriately. Nitrogen is less electronegative than oxygen. So nitrogen should hold the positive charge. And between oxygen and oxygen, it doesn't matter which of those atoms holds the negative charge. So we would say that NO2 has two equally valid resonance forms. And then remember that we can actually approximate this structure honestly, we can approximate this structure using this curved double bond. We can put the radical species on the nitrogen. And now we don't really need to show charges because the negative charge is delocalized. It's not on one oxygen or the other. It's actually a half negative on both oxygens, stabilized by the positive on the nitrogen. So that is the resonance hybrid of NO2. That's actually more what NO2 looks like. It doesn't have a double bond on one side and a single on the other. It has a bond and a half to both oxygens. Whereas SO2 has one valid resonance form. This one, not as valid because it breaks our first rule. It maximizes formal charge. Again, BF3, one valid resonance form because this breaks our first rule. What about carbonate? The one that we showed on the board earlier. How many valid resonance forms of carbonate? All of them have the same amount of charge. All of them have the same amount of octets. All of them have the charges, the negative charges, placed on the oxygen atoms. So all three of those resonance forms of carbonate are equally valid. Essentially, anytime you look at a Lewis structure and you say, why should I make a double bond to this atom and not that atom? Why should I make a double bond to the O on top, not the O on left or the O on the right? You should make a double bond to that other atom. That's a hint that you have resonance forms in your Lewis structure. How fun is that? Coming back to what we said resonance means. Complements each other, kind of on the same wavelength. Literally, opera singers hitting the resonating frequency, matching the frequency that those molecules move with in glass. This is saying same but different. They are the same, but they're different as well. They're different forms of the same structure, and they're both equally valid. And that's the limitation of Lewis structures. It's not a limitation on you. It's not a limitation on NO2. It's a limitation on what Lewis structures can tell us about a molecule.
How would you draw that hybrid for the bicarbonate?
Yeah, I did draw it earlier. The hybrid form, you just start with those single bonds, and then you actually show these dotted lines, which represent not a double, but not a single. If you wanted to have that curve instead, I suppose you could draw it like this. I don't think I've ever seen carbonate drawn like that. But there are some very common organic molecules called acetates. And you can see that acetates, much like carbonate, have a very obvious resonance form. I could place the negative charge on top or on bottom. For instance, this is acetate, which is the conjugate base of acetic acid, that is vinegar. So this is a very common molecule to all of you. And both of these forms are equally valid. So I can draw acetate like this. I can just show this double bond between both of them and a negative charge that is present in that group. This would be harder for carbonate. It looks cool, but I don't think I've ever seen anybody draw it that way. I think the problem is that it actually looks like it has more than just double bonds. It kind of looks like there's triple bonds between these C and O's. That's probably why it's not drawn so much like that. So the dotted lines, I think, would be a better answer there. Questions on resonance? That's the end of Module 9 on Lewis structures. And I hope you're realizing that's why it's a part of the Lewis structure set. Because when you're drawing how a molecule is connected, there is often more than one way you can draw that molecule being connected. The limitation of Lewis structures. Okay. Woke up to some fun news today. You want to guess what it is? It is related to the Nobel Prize. The Nobel Prize in Chemistry was awarded today to these three chemists: Susumu Kitagawa, Richard Robson, Omar Yagi. And it was awarded to these chemists for their work using a material called metal organic frameworks, often called MOFs. And I could not be happier that this came out this morning, because if it doesn't line up perfectly with what we're talking about in lecture today, I mean, I could have paid money for that. Here's what a metal organic framework can look like. These are 6 of the most infamous, groundbreaking MOFs that have been synthesized. MOF 303, MIL 101, UIO 67, ZIF 8, CALF 20, NU 1501. Now these are abbreviations of the framework. You can see these blue shapes are actually geometric faces surrounding metal ions. They're not inherently metal ions themselves, the blue faces, but they represent a metal ion being on the inside. And then these darker lines that you see connecting all these blue faces together, these are organic molecules, hydrocarbon-based structures. This is a snapshot, which means where you see one of these structures end, you can imagine connecting more organics, more metal ions, and expanding the framework. When I was in college, earning my undergraduate degree, I worked with a professor at the University of Wisconsin-Stevens Point, Dr. Mondlock, and he worked a lot with ZIF 8. He was working on solvent-assisted linker exchange. And we wanted to see if you take this material and you put it into a solution of THF, DMSO, water, methanol, and you have different organic molecules, similar but different organic molecules, can you get those molecules to leave the framework and be replaced by new organic molecules? Essentially taking a structure that already exists and modifying it in situ. So we did a lot of research on that, and when I went to graduate school at CU Boulder, I worked in Dr. G.A. Park's lab, and she also worked on MOFs, one of the reasons that I was drawn to her lab. Now, I left my PhD early. I didn't get my PhD at the same point that all of my cohort was defending their PhD proposal. I was defending the work that I had done up to my PhD proposal and then asked to leave with a master's instead. That's because I wanted to be here teaching rather than what they're doing in labs furthering science. This was the paper that came out of my graduate work. And you can see the similar structure. Here is our metal ion. We're working with copper 2+ here, copper 2. We started with a material where the copper was bonded to this organic compound. We called it tetrahydroquinone, THQ. And so this material was referred to as copper THQ. And you can see how the copper binds to the organics. And then again, that would just expand in this infinite framework. These two oxygens would bond to another copper, these two to another copper. And my goal was to take advantage of these empty sites. This copper here has the organic molecules on a plane relative with itself, which means above the copper ion and below the copper ion is empty. So I wanted to take another molecule that could bind to the copper, and I wanted to put that other molecule underneath and above the copper. I wanted to transform the geometry surrounding that copper. And so we titled this From 2D to 3D. We were taking a two-dimensional material and making it three-dimensional. Specifically, Dr. Park is interested in electrically conductive MOFs. MOFs have applications throughout science. MOFs can be used in carbon capture. They can absorb carbon dioxide. MOFs, being these porous molecular structures, have as much surface area within them. Oftentimes, a gram of a MOF can have up to a football field's worth of surface area. And molecules are attracted to each other at the surface. So if you increase the surface area within a sample, you increase how many molecules can be attracted to that sample. So MOFs can be used in carbon capture because carbon dioxide will absorb into the material and then just get stuck around all of those cavities inside of the MOFs. MOFs can be used in drug transportation. You can hold a molecule inside of one of these cavities, ingest a pill, and over time, your body will break down the cavity, slowly releasing the medication. MOFs can be used in catalysis, where crude pollutants come into the MOF, they interact with the materials and the chemicals inside of the MOF, and then they get pushed out, transformed, turned into something less toxic. MOFs can even be used. One of these MOFs that got reported here, this MOF 303, can capture water vapor from the desert air. That water vapor is attracted, again, to the material and its surface area, and so atmospheric moisture gets pulled into those cavities. And then when the sun rises, it heats up this material, gives energy back to those water molecules, and they condense out of the material. They precipitate out. They rain out. And so you can wake up to fresh drinking water in the desert.
Is that what the cloud seeding is?
No. My understanding of cloud seeding is actually like sound vibrations that work in conjunction with chemical nucleation sites to cause clouds to form. Not quite the same, but I like the connection.
You mentioned that most that can, transport some medications. Can they have any protective characters, to protect from acidic environment or they don't interact with the environment?
That's a good question. So in using them for drug delivery, you would actually design the metals and the organic linkers in a way that they do interact with the acidic conditions in the stomach in a controlled way. I want them to break down so that the drugs are released, but I don't want them to be broken down instantaneously. So having them be too inert would not be beneficial. Having them be too reactive would not be beneficial. And you can fine-tune these metal nodes and the organic molecules to get the conditions just right for what you're looking for. So on your handout from today, the left-hand side has 3 metal organic frameworks. One of them is ZIF-8. This is that molecule I worked with when I was an undergrad. One of them is copper THQ, which is the starting material to the compound I used in graduate schools. You guys need them. Thank you. And one of them is copper THQ50, which is that 3-dimensional molecule that I was trying to synthesize in graduate school. We're going to apply what we learned today on molecular geometry to these metal centers. And then on the right-hand side of this sheet, you'll find some other more common organic and inorganic compounds, and we're going to apply molecular geometry to the atoms inside of these organic compounds. At the bottom, and I know it looks a little awkward because it kind of overlaps, it bumps up really close to acetylene. On the bottom, I actually have 2 images of the heme group in hemoglobin. You guys know where hemoglobin is? In your blood. It's responsible for what? Good. Transporting oxygen to your cells and making sure that you have energy to create. I know that it's not great in this photocopy. We're going to be looking at the iron in heme on the left versus the iron in heme on the right and determining the 2 geometries that your iron in heme has. Unfortunately, with this document, I could not find heme free of oxygen and heme with oxygen. But there are 2 states of heme with oxygen, heme without. The structure on the left actually is heme with oxygen, but it doesn't show the histidine that attaches to the bottom of iron. So this is the same geometry as heme without oxygen. It's just not the heme without oxygen, if that makes sense. I picked this because I wanted to show you the 2 important stages of iron in hemoglobin, the 2 geometries that iron takes on in hemoglobin. And we're going to talk about what those are. I'm running a little long-winded on this, but I wanted to just show you some other interesting things about these MOFs. Here is some tunability of MOFs where the linker is being changed for something longer and longer, and what you can see is that the cavity inside of that material is increasing because of that. Here's another interesting image of MOFs. This shows you a little bit more atomically how those metal nodes attach to everything. This is showing you those geometric faces around the metal nodes, and then this is showing you at a larger scale what that framework looks like. Again, tunability of these MOFs. Capture something and then change its conformation so that those gases are expelled so that you can store things like hydrogen at pressure without being pressurized and then expel that hydrogen. And then again, the complexity that all of these organic linkers and metal nodes can have. This is an organic molecule, and it creates its own geometry relative to these metal nodes. The tunability of these materials is incredible. So it was cool to wake up today and find out that the main part of my undergraduate and graduate research and what is being called the material of the 21st century has received the Nobel Prize for Chemistry today. All right, before we dive into this worksheet, we need to do a little preamble on what molecular geometry is. And before we do that, I want you guys to get a break from listening to me talk. So why don't you take 5 minutes to get up, move around, and get your blood flowing, and we'll come back in so we can go through this worksheet. That's a good question. I think you could find these materials in nature, but they wouldn't be like a common source. That is to say, like, the odds of this forming are non-zero, for sure. But they're not, they're most commonly known for their synthetic things. Yeah. If you watch the recording, it'll help you fill out this bottom part a little bit more. This is what we did yesterday, but there's not a lot of information on it, so without the recording, it's a little less useful. Just so you know.
Were you able to get the, so in the actual experiments, was there atom molecule attached to that number on both sides?
Yeah. Yeah, and we would measure it by taking the final product, taking its XRD, its X-ray diffraction pattern. We would shoot X-rays at it and see how the molecule is arranged by this X-ray diffraction. And then we would say, okay, the structure is preserved. Whether it's the same or new, it's preserved. We hadn't like deteriorated material. Then we would take that sample and we would digest it in acid, and we would put it into an NMR instrument, nuclear magnetic resonance, and we would look for key signals from the original organic linker and from the new organic linker, and we would be able to quantitate how much of those signals we had to say, I had 100% of this molecule. Now after it, I have 20%, or 80%, or 50%. So we could quantify the exchange. And then this was kind of the process of, are we preserving the integrity of the material while substituting the organic linker? We wanted to do both. Yeah, it did. I don't actually remember numbers off the top of my head. Like, it was never 100% exchange. And I don't think there was like a clear end goal. It was more like proof of concept. Because like I said, when you diversify that organic linker, you change its chemical interactions, physical interactions. You change what your material is now going to be able to do. So you can get something that's maybe more beneficial out of that. It is cool. All right, are you ready? This is Module 10. On molecular structure and polarity. We have been drawing structures, Lewis structures, without necessarily any concern for how it actually takes up three-dimensional space. We've just been drawing them flat. Now what we want to do is consider how all of those regions around an atom, all of those regions containing electrons, interact with each other and force the molecule into some three-dimensional shape. We will be using VSEPR theory, that is valence shell, electron pair, repulsion. Those of you that were in my lab last week, when we did the Lewis Structures lab, how is this actually pronounced based on how it's spelled? VSEPR, which doesn't have the same ring to it as VSEPR. So you'll often hear this referred to as VSEPR theory, despite being valence shell electron pair repulsion. Remember, electrons repel each other, except for when they pair. Because why would you want to repel something that has an opposite magnetic field to you? But once they're paired, then they repel each other. That's why we're talking about electron pair repulsion and not just valence shell electron repulsion. This predicts bond angles and three-dimensional shape. That's the role of VSEPR theory. This is based on interactions between two types of things. We call them electron regions. Bonding regions and non-bonding regions. We're going to look at how bonding regions interact with each other and how non-bonding regions interact with each other. Those of you that have done the reading and were at lab last week, you might recognize there's a different word you can use instead of region. Domain. I don't know, that just seems like a fancier word. Feels very archaic, like Tolkien domains. Bonding regions. What types of bonding regions can you have? Well, you can have a single bond, a double bond, or a triple bond. These would all just be considered a bonding region, regardless of how many bonds are in that region. Relative to a central atom, is there a bond? Yes, it's double, it's triple, it's single. One region. Does that make sense? It's very easy to say, I'm going to count all of the bonds and give them each their own region. But if you're looking at a region between two atoms, it doesn't matter what type of bond is there, it just matters that it is a bond. Non-bonding regions, these are what we call lone pairs, LP, or they can be radicals. What is a radical again? An unpaired electron. The three-dimensional shape that we get, we're going to refer to it as geometry. That's earlier what I was talking about with the MOFs. I was talking that those blue faces show their geometric faces. There's two types of geometries. There's an electron geometry. Shows the arrangement of all electron domains, all electron regions. You look at a central atom and you describe how its bonding regions and its non-bonding regions are oriented in space relative to that central atom. And then we have molecular geometry. This is always some subset of the electron geometry. The molecular geometry shows the arrangement of the atoms. Now the atom's arrangement in space is dictated by non-bonding regions. The atom's arrangement is held by bonding regions, and bonding regions are impacted by non-bonding regions. So we'll take this overall arrangement of all regions and then ignore those lone pair and radical regions and just look at how bonding regions are arranged. You cannot determine molecular geometry without first determining electron geometry. Electron geometry has to come first, and then you look at a subset with the molecular geometry. Here's what we get, this table. You're not going to receive a table like this on your midterm or your final. So I would recommend printing something off to use for your unit test, copying down something like this until it's familiar to you and you recognize it. Or taking the ones that seem to escape you the most and confuse you the most and putting those onto your cheat sheet as reminders. So you'll notice that we go from 2 to 6 electron groups, electron regions, electron domains. Our second column tells us how many of those regions are lone pairs. None. Now take one of those regions and make one lone pair. Now take two of those regions as lone pairs. 3, 4 of those regions. And we'll look at the three-dimensional shape that's created. One interesting thing about this graphic, when a central atom, that's being represented here by E, when a central atom has 2 electron groups, they both have to be bonding regions, otherwise it's not a central atom. A central atom is one that is connected to more than one other atom. So there is no geometry where a central atom has one bonding and one non-bonding region. It doesn't happen. Only when there's 2 bonding regions. But when we get into 3 electron regions, 2 of them can become bonding while one of them is non-bonding. And you can see that in this 3 bonding regions, they all want to repel each other as far as possible. There's actually a mathematical principle here. Do you know how many dimensions a dot has? A point. How many dimensions does it take up? A point has no dimensions. It doesn't exist on a line. It doesn't exist on a plane. It doesn't exist in a field. A dot is dimensionless. Okay? 0 dimensions. What about the connection of 2 dots? It doesn't matter how you arrange these 2 dots. You will always find that these 2 dots define one dimension. They define a linear geometric space. So when a central atom has 2 regions surrounding it, we say that the geometry between them is 2D. Again, these electron pairs that are bonding are repelling each other. They want to be as far away from each other as possible. How far can they get? 180 degrees, which lines up the 3 atoms in a linear geometry. If I have 3 dots, and once again, it doesn't matter how you arrange these. You could take one of these dots and put it in the middle of the room. 3 dots will always define a plane. And a plane is how many dimensions? 2. So we refer to that as planar. And this is true. Go ask your math professors, ask your math friends. 3 points define a plane. Relative to your central atom, these 3 groups want to be as far away from each other as possible. That's 120 degrees apart. That's the maximum. And they will always, always exist on a plane. Those 3 groups define a plane. So because they arrange themselves 120 degrees away in the shape of a plane, we call that trigonal planar or trigonal planar for the triangular nature. It's once you get 4 groups that you start to be able to do some crazy stuff. And this is where it actually gets very hard to show you what's going on. So we introduce some perspective. This is art class now. When we show you this filled in wedge, we are saying that this group is coming towards you. It's coming out of the plane of the board and it's oriented at you in space. I just can't show it actually coming towards you because that's a 2-dimensional board. We're trying to represent 3-dimensional things on 2 dimensions. This dash is showing something that's going away from you. So what do those lines mean that aren't wedges and aren't dashes? What are these? They're just showing us where that region is and that it's in the plane of the board. These two lines are in the same plane. These two groups are in the same plane. Whereas this group is coming towards you out of the plane, and this group is going away from you. Now, I think that linear and trigonal planar, those names make sense. But the name for this four-sided shape is called tetrahedral. Does that mean anything to anybody? Tetra is 4? How do you know that? Did the reading. There's actually a very common game that tells you that 4 means tetra. Tetris, the game with pieces that have, all of the pieces have 4 components, right? You can arrange them as a square, as a line, as an L, a backwards L, as the little T shape. Tetris, a 4-component shape. That's where the name comes from. So, this first region is the large set of electron geometry. It doesn't matter if these are all bonding or lone pairs. When you have this number of regions, this is the electron geometry. Everything beyond then is called a subset. This compound that is bent 109 degrees has a tetrahedral electron geometry. And you can see that it's got these 2 things in plane, 1 towards you, 1 away, 2 things in plane, 1 towards you, 1 away. But its molecular geometry, only considering the arrangement of the bonded groups, is just bent. That's impacted by the lone pairs. If there were no lone pairs, what geometry would it have? Linear. But the lone pairs impact the molecular geometry. So to try and sum this up, before I let you loose to determine molecular and electron geometry on that worksheet. Electron geometry is a large set. Molecular geometry is a subset within electron geometry. And there are some overlapping geometries. Here, where I have 6 electron regions, only 2 of them are bonding, that's linear. The same as when I had 2 bonding regions only. Here, where I have 5 electron regions and 2 of them are bonding, also linear. Here, where I have 4 electron regions, 2 are bonding, bent. 3 electron regions and 2 are bonding, bent. 6 electron regions, 3 are bonding, T-shaped. 5 electron regions, 3 are bonding, T-shaped. There's this overlap of how the molecular geometries are arranged, even within these larger sets of electron geometries. Are you okay with that? That you can get to the same geometry in different ways? Here's another resource that I plan on sending to you guys. Oops, here it is. This tomorrow, probably, in my announcement. This is called Symmetry at Otterbein. They take these molecules and they render them in 3D so that you can see their molecular geometry. Now, this website doesn't actually go through and tell you
what their molecular geometry is. It simply shows it to you. But I think that you could probably figure it out. What's the molecular geometry of this yellow atom? Bent. Yes. What is the molecular geometry of this yellow atom? It's not tetrahedral, but that is a good guess. It's not T-shaped, but that's not a bad guess either. Yeah, Ryan, you want to hop on this end and I'll hop on this end? And we can seesaw? Could have called it teeter-totter. How many of you call it teeter-totter? Okay, I'm not alone. I actually had a British friend that I said, oh yeah, we call that a teeter-totter. Hearing her say, teeter-totter, one of the coolest things. If this is a seesaw shape, a teeter-totter molecular geometry, how many lone pairs must it have? Oops, sorry.
Yeah.
How many electron regions does it have? How many lone pairs? Sorry, that was the answer. If we know it's a seesaw shape, how many lone pairs does that central atom have? One? Because we see here the seesaw shape only shows up once. That's not a shape that comes any other way. And that's when you've got these 4 bonding regions, 1 non-bonding. Does this image look as much like a seesaw? No, I think this orientation looks more like the seesaw. So you know these chemists were just having a fun day, moving molecules around and then trying to come up with names for these shapes. So here's what I want you guys to do. Oh, actually, there is another website to show you, which is the one that you all used during lab. If you weren't in lab, this is why I want to show it to you. I'll link this in the announcement this week as well. When you come to this simulation website run by the University of Colorado at Boulder, you will find that you can build molecules. Somewhere you will find it. Oh, I see. I'm looking in this. They allow you to change how many lone pairs you have, how many bonding pairs you have. And they let you look at it in 3D. So let's say, I don't want that. Let's say that I have these 4 electron regions and 3 of them are bonding. First of all, you can grab these groups and you can move them around. And do you see what they do when they move? They repel each other. They're repelling until they get into their lowest energy conformation. And then at the bottom, you can have it tell you electron geometry and molecular geometry. So if you want to quiz yourself, you can build something first. Let's say I want to put in 3 more lone pairs. Now I need to figure out what the molecular geometry is. T-shaped. And the electron geometry. This is an octahedral electron geometry. Okay, one more thing actually before I let you loose on this. There is this weird thing in this big class. Tetrahedral literally means 4 faces. We're looking at 1, 2, 3, 4. Octahedral means 8 faces. Confusingly, the octahedral has 6 groups, 6 electron regions, not 8. Where the tetrahedral has 4 electron regions, just like 4 faces. That's confusing, and I just don't want you to get tripped up. And then here, where we have something that has 6 faces, we don't call it hexahedral, but we call it trigonal bipyramidal, because it's a triangular base with a pyramid on top and on bottom. But we don't call this square bipyramidal, and we don't call this pyramidal or trigonal pyramidal. Honestly, I wish I could have been in the room where they named these so I could tell them to just stay consistent. Pick a lane. I would have actually called this trigonal pyramidal because here we have square pyramidal. Here we have trigonal bipyramidal. I would have called this square bipyramidal. And I'm sorry that I can't name them for you, but you have to name them the way it's based on this. All right? So please, oh, one more thing. Are these graded? The sheet I handed out Monday, this sheet today? No. This is just the activity for you guys to apply what we're doing. You're not turning these in, you're not getting a grade for them, just using it so you don't have to try and draw these out. I want you guys to spend 5 minutes on the left-hand side maximum and 5 minutes on the right-hand side maximum. On the right-hand side, there's multiple central atoms in some cases. I want you to find the electron and the molecular geometry for all central atoms. This is a bit of a confusing thing about the name molecular geometry. It's subjective to a specific atom. Many molecules, most molecules, have multiple molecular geometries. Does that make sense? The molecule doesn't have one molecular geometry. An atom has a geometry with how the molecule is arranged around it. Atoms have their own molecular geometries. Are you okay with that? So you'll look at each atom to determine its molecular geometry, each central atom. When I say the right-hand side, I actually also want you to do heme on the bottom. Use this graph. Figure out electron and molecular geometries. And do this in pairs or in groups of 3 so that you guys can bounce things off of each other, ask each other questions, and I'll be coming around to walk through and answer things. Oh, sorry. Oh, you wanted one? Yeah. Yeah, go for it. Jackson, I encourage you to work with Bella and Nicole.
Yeah, well, I don't know if that's what you said. Yeah, I'll keep on like talking. I actually myself.
Fair enough. Yes. You're looking at a wedge and a dash. So this is showing you coming towards you, going away from you. Correct. Good question. If it was tetrahedral, I think you'd agree it would have 2 things that are in the plane of the board and 2 things that come out or away. But what you actually see looks more like this, doesn't it? 2 things coming towards you, 2 things going away from you. Here? But it's not just 2 things coming off the copper, is it? It's 4 things. So you've got 4 bonds. Those 4 bonds are either going to be this, this, or this. You've got 4 bonds, and you have to decide which of these molecular geometries you're actually seeing.
So it is.
Mm-hmm. I think the question is,
Wait, square plant is the electric.
Correct.
And so the electric chemistry would be changed.
No.
I agree that it makes
No, because molecular geometry, Blake, is a subset.
So it would be
Correct. What do you not see there? The lone pairs. Correct. Good guess. But notice how you've got two groups coming towards you and two groups going away. And that is what our octagonal geometry looks like when we scoot over two things really important. Yeah. Rather than which looks more like this one is this one actually
Yeah, but we're just naming like what structure. Some might have like more than one central, and then name the shape for each.
I don't think you guys need the top one, right?
okay. Well, just from one central atom. You want to look at this carbon. It's got 4 bonds. This carbon it's got 3 bonding regions. This oxygen, 2 bonding regions.
But it's like
Multiple central atoms. Correct. You need to tell me that molecular and electron geometry all
Yeah.
you don't need to.
because that has
That's right.
then it would have
See if you can.
Our only shapes are only opposite.
so that can't be that or angular. Maybe that or angular. Because it doesn't only have 4 bonds, but it has 2 lone pairs. And it does still have 2
That's a good question, and actually it doesn't show the lone pairs here.
I would
These will all, and the problems that you have will have lone pairs.
5, 6.
But it's just much less common in things like lungs. This one? No. It's not square root. It's not square
Oh, I see.
How many electrons are in this?
Because I don't see anything else that like has the that it's
Correct. So we're in that bottom row. And how many of them are lone pairs?
or it has like
None of them are. They're all 6 bonded. So it's what?
because I think this like
No, you can do electron geometry. That kind of gives you a bigger picture.
This is the one that tries to oxygen.
Square planar because it's not showing the
Yeah, so it can't be bent or angular because you'll notice that has 4 electron regions where only 2 of them are bonded. But this has 4 bonded.
And then you're
Do you agree it has 4 bonding regions, the copper?
yes.
That means if it has 4 bonding regions, it's either this, or this. This has 4 bonding regions. This has 4 bonding regions and a lone pair. This has 4 bonding regions and 2 lone pairs.
Are the bonding regions being indicated by the X's?
Yes, and lone pairs are indicated by the dots.
Oh.
Yep.
Okay.
Which of these geometries do you think the copper looks like more?
Well, it doesn't
It doesn't show the lone pairs. That's true. But what about these wedges and dashes?
It looks more like a square.
So what can you infer about lone pairs?
That it probably has one on top and one on bottom.
It might have one on top and one on bottom. But the molecular geometry agrees with this. Good. You bet.
Yeah, they're basically. And then drop is it, do you want us to do like a more
Well, so this is actually just looking at binary again. But for these, if you have more than one central atom, look at all of them. Find a central atom. Determines electron and molecular. Yeah. So for zinc, and it reads all your
So we have
We'll call it four. And look at how it's
yeah. So I'm doing it for these. So I see.
Because there are two options for bend.
I decided. And
But with
then
5 bonding regions, or sorry, with 4,
yeah.
We have a number of options.
Nitrogen, and then there's that oxygen.
4 bonding regions, but it doesn't look like that. 4 bonding regions, but it doesn't look like that either. 4 bonding regions, and it does look like that. 2 that are coming towards you and 2 away, creating a plane in the shape of a square. Square planar. You can't see the lone pairs, but now you know that its electron geometry is on because it's a square planar. All right, guys, I want to go through some of these with you before we move on. Most of you looked at this zinc atom first and very readily said, that's a tetrahedral center. That's ZIF8, and ZIF8 does have that tetrahedral zinc geometry. And then you got to copper and you said, what the heck is going on there? It also has 4 bonding regions, but it doesn't look like the zinc above it. And there's no electron lone pairs that are shown on the copper. So a lot of you took that to mean, well, it must also be tetrahedral because all I see are 4 bonds. And I will say this copper situation is not similar to how you're going to see it on the unit tests or the midterm. You're going to see it more like what you see on the right-hand side of your sheet, where you have an actual molecule, or you're just going to be given a chemical formula. You have to know what the Lewis structure looks like. You have to draw the Lewis structure and then determine its electron and molecular geometry. That's where this stuff starts to compound on itself. Draw a structure, answer what its geometry is. So this copper that we're looking at, it's not like a problem you're going to have to answer, but notice the geometry. 2 groups coming towards you, 2 groups going away. It's not this 4 bonded region or shape. It's not this 4 bonded shape. It is this 4 bonded shape, square planar. So you could take that to infer that copper has other sites that have electrons in them above and below the copper. What is the electron geometry? Not molecular geometry. What is the electron geometry of this copper center? Octahedral. And its molecular geometry, square planar. Now remember, this is the starting material I was telling you about that I worked with in grad school. And this was the product that I was trying to make, copper THQ BIPI. What is the electron geometry here? Octahedral. Copper maintained an octahedral electron geometry. What is its molecular geometry? Octahedral. So a good tip for you is that if a central atom has no lone pairs, and again, you are almost always going to see those lone pairs. If a central atom has no lone pairs, its electron geometry is its molecular geometry. All of the regions pushing each other away are bonding regions. Let's look at iron quick on the bottom. I know some of you didn't get to this one yet. How many electron regions surrounding the iron here? What can you obviously tell? The nitrogen and O2, oxygen. So 5 regions. But do you think that it looks like this, trigonal, bipyramidal? No, definitely not. What does it look like? Square pyramid, square pyramidal. And you can see that. The 4 nitrogens in the porphyrin ring, that's what this large ring is called, a porphyrin. These 4 nitrogens are all in the same plane, creating the base of a pyramid. And oxygen sits on top of the iron, making square pyramidal. Remember, this doesn't exist so often. What actually exists more often is that histidine binds to iron on the bottom. Still square pyramidal, just upside down. When you have histidine and oxygen, what is the electron geometry and molecular geometry? Octahedral. So, octahedral in the beginning, where it's square pyramidal, octahedral at the end, where it's also octahedral. Those are the 2 geometries that iron takes on when it's transporting your oxygen. Square pyramidal molecular geometry, octahedral electron, octahedral, octahedral electron and molecular geometry. All right, let's look at some more common molecules. Acetic acid, vinegar, has how many central atoms? 3 central atoms. This carbon on the left, carbon in the middle, and the oxygen on the right. Which means that there are 3 electron geometries and 3 molecular geometries that can be applied. Carbon on the left, tetrahedral electron and tetrahedral molecular. Carbon in the middle, trigonal planar electron and trigonal planar molecular. No lone pairs on those carbons. So their electron geometries are their molecular geometries. What about oxygen here? Tetrahedral electron geometry, bent molecular geometry. Good. Why don't we look at the S in sulfuric acid, the sulfur in sulfuric acid. What is its electron geometry? How many regions around it? Just 4. Tetrahedral electron geometry. How many of those regions are non-bonding lone pairs? None. So its molecular geometry, also tetrahedral. Doesn't it look flat? But it's not. It's 3-dimensional. The sulfur sits here with double bonds to oxygens and then single bonds to the OH. That's what sulfuric acid actually looks like. Let's look at the sulfur in thionyl chloride, SOCl2. How many electron regions do you see on this sulfur? 4. 3 bonding regions, 1 lone pair. So its electron geometry, tetrahedral. But its molecular geometry, four electron regions, only 3 bonds, trigonal pyramidal. And then lastly, acetylene, which is a common fuel if you're using a torch or welding. What is the geometry around this carbon atom? linear. 2 electron regions, they push each other 180 degrees apart. All right, what we didn't get to today in terms of molecular structure and polarity was actual polarity. So we're going to have to pick up there on Monday. We're going to talk about polarity. Here's a tip for you. Polar bonds can lead to polarity, but not always. So if you want to get a head start on your Module 10 checkpoint over the weekend, you're more than welcome to. I will be shifting due dates so that it aligns more with what we do next week. We're going to go through Module 11 on Monday. We're going to try and work fast. Unit 5 can be done in one day, just it's not fun. So we're going to try to speed through the rest of Unit 4 and get into Unit 5. All right, guys, have a good weekend. I'll see you on Monday.